Yeah, so let's start. Okay. Yeah. So this is week two discussion for the course of theory of production processes, and today we'll be talking about different aspects of technology of pattern making, which was content of your second week course material. So as usual, we'll discuss some concepts, and along with that, we'll take some problems. Hmm. Okay. So yeah, let's get started. Hmm. So like we discussed majorly uh, on these things, what you call uh, pattern materials, which type of materials are used, then pattern allowances, different types of patterns, then molding sand ingredients, some sand testing methods, some sand molding methods, core making properties, etc., and different types of cores. So it was a quite uh, heavy kind of a week, you can say. Uh, so let's go one by one. Hmm. I'm just seeing the previous year questions uh, and some numericals, because if it is all theory, it becomes slightly monotonous. So just give me some time. Hmm. Yeah, there are, you know, there are few interesting questions on shrinkage allowance, etc., volume of the casting after shrinkage, then yeah, other than that, mostly the questions that we already saw in the previous class regarding the solidification time, those things are, I mean, these are the favorite topics of your examiners from casting topic. So first we already saw, which is solidification time, etc. Then today we'll see some examples on allowances, etc. In the next week, maybe when we'll study the gating system design, then there are certain other types of uh, numericals that will come in that topic. So other than that, we have to cover some theoretical uh, topics, uh, and directly. I mean, you will not get numericals on all the theoretical topics because it's the nature of these topics. But what happens is, uh, you know, uh, you'll get questions in which four options will be there, and they will be from each of the theoretical concept, and then you have to choose the correct one or the wrong one, or other type of questions could be match the pairs kind of things. You'll have two columns, and each column will have a certain uh, questions or certain theoretical aspect behind it. So we'll see. Okay, so let's start. The first topic is about the pattern materials, and this was also discussed by professor in the class. But oh, sorry. But we'll just summarize this, because again and again you can't everything you cannot. Uh, speak again and again, because I'm assuming you have already studied the class notes, etc. So yeah. Okay, so 1 second. Okay, so basically, there are different type of casting materials, but majorly it will be wood and uh, metals. So we'll study as a table. Okay, and then there are certain uh, smaller things also, such as waxes, and some organic organic materials for binders. Sorry, for pattern making. But these kind of things, they melt as you pour hot liquid metal on that. They tend to melt. Sorry, not melt. First they melt, then evaporate, or sometimes they can sublimate also, depending on the conditions and all. Then the gases are, since you're uh, you know uh, molding sand, etc., they are permeable structures. These gases will be released into the atmosphere, and the space or the matter volume occupied by these wax and other type of binders, they will be occupied by your what do you say, molten metal, and then it will be solidified. Okay, so let's start with the pattern materials, and we'll discuss the important ones, which as I said. So we'll make a table here. Okay, so first category is the famous one, which is wood, or maybe I can use some other color for this. That will be better. So you have wood, which is very common, and then you have some metals which are also considered as good choice in some cases for pattern making. So we'll list down some things about, or some uh, positive things about uh, wood as a pattern material. First of all, it's cheap, you know, as compared to metals, easily available. Uh, you know, you should understand that uh, if you need, very good quality wood like mahogany or teak or something, they may be costly, but typically for normal casting, uh, casting methods, you can use normal woods also. So in some very professional or specialized setups also, only you need mahogany and teak kind of woods. But other than that, if it is not that critical, you can use normal wood also. So that's why I'm writing it is cheap, easily available, non-corrosive. So with wood, you'll not have any problem of corrosion. Light, light in weight, or you can say, you know, lower density. So when there are big casting products to be made, you cannot use metal, because if you make the whole thing by metal, you know, it will be very heavy, and the handling, etc. It becomes difficult. Okay, so it is easily machinable also, because you can cut or grind, etc. easily. Wood's not that difficult to do that. Since they're lightweight, uh, you know uh, you can lift, and easy to handle, basically easy handling. Also, it's not they'll not have that uh, corrosion, etc. So surface holding surface and all is also not that difficult. And these are the advantages. What are the disadvantages? Uh, Prone to dimension changes, and the most important factor that affects its dimension is moisture content. So depending on moisture content and the type of wood that you typically use, uh, you can observe 8 to 12% of volume changes also. If it is humid condition, then the wood will swell. If it is dry condition, then it will shrink. Okay, so that is the problem. Okay, then the surface finish is like average surface finish you can get with the wood as a pattern material. If it is good enough for your application, then fine, but in some applications you need very good quality surface finishing from the cast, so that you cannot get from the wood as a pattern material. And because of this, volume changes and surface finishing, etc., it is not suitable for mass production or large scale continuous productions, because there you need reliable patterns, uh, because you cannot keep on checking every each and every casting whether its volume is same or not. So yeah, so that's some of the disadvantages of wood as a pattern material. And then let's come to the metals. So you know metals also, if you consider a big chunk of them, they are also non-corrosive only. I mean, they don't get corrosion that easily, but you know majorly non-corrosive. But eventually, if it is not like SS or anything, they will eventually corrode. But you can reduce the rate of corrosion by using some tricks. Uh, then they are dimensionally stable. So the disadvantage that you get in the wood case, which is moisture content, and that leads to dimensional changes. Here you don't get that because metals don't change their volumes based on the moisture content that they're around, and you'll get improved surface finishing or finish. So therefore these are good for mass production. Okay, so in mass production you'll see they use metals as the pattern making material, whereas on a small scale kind of setup they'll use wood. Okay, but then what are the disadvantages? Typically these are heavy, that is one. Therefore, uh, you know, difficult handling as compared to wood. And some are prone to, some are prone to corrosion also. So I have said that mostly they are not, but some are prone to corrosion, such as cast iron. So these guys corrode. So that is also one of the drawback. And these are economical because you need large costs to procure metals and machine them, etc. So these are economical only for mass production. So for small scale productions, you cannot or you should not use these because from economics point of view, it doesn't make any sense. Okay, so this is regarding your pattern making materials. And as I said earlier, there are some waxes, etc., and they are like small set of pattern materials, but yeah, they do exist, and there you can think of it on your own, such as uh, you know they usually evaporate or sublimate when you pour the liquid metal. Investment casting is what typically they are used in. Okay, so but you should know one thing, you know, to make metal patterns, first you have to do with wood only. So, this is like if you think of mass production metal patterns are better, but that metal patterns are made by wood patterns first. So there is a that original wood pattern is called as master pattern. So sometimes they ask this type of questions also. And then there are plastics, etc., polystyrene, PVC, thermocol, which are waxes. They are third category. Okay, so that is that. Then what else is there? Yeah, then we studied different type of allowances, right? Or shall we take the patterns first? 1 second. Yeah, types of patterns we'll take first. So depending on the type of pattern that you have, the whole thing changes, because it's not like it's a simple process. You have a lot of things to consider when you consider patterns, etc. So we'll see one such a case. So yeah, and in wood, before we move on, in wood there is something called as seasoning. So that is a process in which you stabilize the moisture content of the wood. But yeah, I mean, it's a headache. That's the point. That is a problem. Okay. Then types of pattern. One is single piece pattern, which is also called as simple pattern. You know, so these are like easiest to make. So types of patterns. One second. Yeah, 1 second, guys. I'll drink some water. So yeah, first is a single piece or simple pattern. Just see. Yeah, so they are called as solid or single or simple piece patterns. And as the name suggests, you can guess these are the simplest ones. No big deal. Uh, you know, and one thing is, for these kind of things, these kind of patterns, at least one face of the pattern must be flat. So that is the underlying assumption. So the face which is flat, you keep that down and you make the pattern. So that is when you get the easiest ones. Okay, but life is not that simple. So in other cases, you'll not have such simple patterns. The second pattern you'll have is called as a split piece pattern. So as the name suggests, uh, as the name suggests, you'll have to have two pieces in this case, because you cannot make this pattern in one piece. For example, the common shape that is considered is something like this. So you cannot make this in a, you know uh, as a simple piece pattern, because then how do you remove this pattern when you want to pour the liquid metal? So therefore, what they do, they typically divide it into two parts, and you know like this. You can divide this, and then it becomes a two-piece pattern. This is called as cope, and the bottom part is called as drag. And they usually, use some pins to keep these two cope and drag components together. Those are called as dowel pins. Okay, so these are some of the uh, common terminologies, and in some problems, they typically ask, you know, uh, what is the instrument, or what is the equipment that keeps scope and drag together. So that is your dowel pins. And there is no, though, see, there is no limit that only two, only cope and pattern could be there. There can be more than two pieces also. Okay. So this is used for complex shapes. That is first you can understand, which includes sphere, dumbbell, etc. So the dumbbells that you use in gym, not the new ones where the weights are bolted, but the previous or the earlier ones, if you remember, they typically were made by split piece pattern casting. And yeah, the important thing that you should remember is, uh, you know, it can have more than two, can have more than two split pieces. Okay, so in this image, I have shown you the two ones which has scope and drag, but not necessary. You can have more than two also. Depends on the shape that you want to cast. Okay, so that is the main objective of this point. Then third, you know, you have loose piece patterns, and as the name suggests, you have to make this patterns using some loose pieces, and these are used for patterns, or you may call castings also, used for patterns having internal projections or undercutting. Okay, so or undercuts, not undercutting, undercuts. For example, something like this. You want to make something like this. So this part is the headache. Let me just highlight it. This part, because if that part is not there, it is simple pattern, right? But this is where, for this, for making pattern for this, what you do, you make bigger one separately and the smaller one separately. So this is the loose piece that you have to put in. And once you ram the sand, you remove the big pattern, and then slowly you remove the loose piece using lifter. So there is one instrument called as a lifter, and then you get the uh, this thing. You get the pattern. But the problem is, it's not, if it is too complex. So if the limitation is, if loose piece also have complex shapes, let's say loose piece Here the loose piece was simple, right? But if loose piece has complex shape, then you cannot use this method basically. Then this method is not feasible. Then what do? You go for wax molding. So, so in that case, you have to use wax instead of this thing. And another thing is if loose piece width is large, then you cannot use lifter also. Then you are stuck. So not good for large width loose pieces. So there also it is limited. Okay, so these are certain things about the loose piece pattern. Then after that, what was it? One second. Gated pattern. So this is, we'll see more of this in the next class also. So there you'll analyze this in detail, because this is the uh, one pattern making method or type of pattern which is widely used, because it eliminates the uh, time required for hand cutting of runners and gates, because you use common runner for multiple products, casting products, and that saves you a lot of time. So you'll have a, one second, you'll have, single runner like this, and some arbitrary shapes I'm drawing. But the thing is, you have single runner. So runner is like, common uh, pathway which provides liquid metal to these patterns, and each pattern will have its own gate. So this is called as gate for this pattern, and therefore the name, which is called gated patterns. So the advantage is, if you want to make these patterns individually, it will take a lot of time, because we'll see in the next class that you have to give runner, riser, etc., etc., and other things. So what they do, they simplify or they mass produce these kind of patterns, and therefore time required for cutting of runners and gates is reduced. So which means improvement in productivity or efficiency. And that is the whole reason why we study this in detail in the next week, because you know in most of the uh, industries this is used. Okay, so then you have match plate pattern. uh, you know but before that, yeah, one limitation is you know not for not suitable for complex pattern shapes. So you can make like simple pattern shapes, but if it is too complex, you cannot use gated patterns. Okay, so then you have to see whether wax or centrifugal or whatever it's required. Okay, then you have match plate patterns. Okay, so you know uh, thing is, typically if you want to make something like this, say let's say hexagon or something like this, what they do, uh, they will make this top half like this, bottom half like this, and you'll have one match plate of same material, okay, like this. And you know uh, once you remove the match plate, then you remove the pattern also, and then what happens, your runner, this will be plate initially like this, but becomes runner after you remove it. And runner becomes integral part of your pattern, or uh, like that, so like that. So when you finally pour, like if you remove the match plate, 1 second. One second. Yeah, typically runner becomes the integral part. Uh, yeah, you don't remove the match plate. What you do, your runner is basically not here. Match plate is okay, but you'll have a runner somewhere here, like that. Okay, and then like that. Okay, so runner will be separate. So basically, this is also like split kind of thing only, but the advantage with this is it is used for small size complex shapes in mass production. Okay, so where this is where match plate patterns are used. Okay, so then the next one was sweep pattern, and as the name suggests, if you have used any of the uh, CAD drawing model or something, you will understand that uh, you know sweep function, there it is, always there. Okay, so what is there, basically if you want to make a cone like this, if you want to make this cone by casting, so this is your 3D object, right? So what they do is they take a triangle of same radius, bottom radius, and same this thing. So if this is your R, this is also R, but this is a 2D plate. They put it in the sand and they sweep it. Okay, so you know this is swept 360 degrees and you get a cone. Okay, so it is not like this, but they will revert it. So you'll not make cone never like this. So cone will be always circle on the top, because otherwise you can't remove the pattern out. Okay, so that is the sweeping pattern. So the advantage is, it is uh, suitable for axisymmetrical type of patterns. Otherwise, if it is not symmetric, then you can't use this technique, because then you can't sweep, right? You don't have anything. Okay, so that is one. Hmm. we'll see later about cores, etc. Chaplets. Okay. Then there is seventh, which is follow board pattern, and this is used for some thin type of patterns because they don't have enough strength. So this is for structurally weak patterns, because if you have patterns such as some thin plate or shape like this, if you just put it in the sand and if you ram it, there is a chance that it will deform. So what they do is they make one supporting board which is called as follow board here, which is the terminology. So that board, the job of that board is to provide strength to the pattern during ramming. Okay, so this is the main thing. And then the other things are straightforward. I mean, then you'll put some sand here, and then you ram it, and then so those things are pretty much standard ones. Okay, so yeah, these are typical uh, types of patterns that are there. Let me just see if I missed any. So yeah, sometimes yeah, you'll have something called a skeleton pattern. So as the name suggests, this is used for large scale pattern making. So as I said in the beginning of the class that wood is the better choice for large scale pattern making. That is true, but sometimes you cannot make the log of wood also very big because you may not have it. It will be difficult to procure it, etc. So what they do, they will make a hollow structure. So basically, like aircraft, what do you call, aircraft sitting area or cabin. So from outside it looks like cylinder, but inside it's hollow, right? So this will be like hollow cylinder kind of thing, and you'll have, let's say, something like axisymmetric type of thing, and you'll have one rib-like structure. So inside you'll have some supports like this, and there will be one central support, which is these are called as ribs of your skeleton pattern, and then you put it in the sand and then you ram it, etc. Whatever you want to do, and for example, you can take large dia pipes. So these you must have seen. These are always you know what do you say, big sewer pipes or oil pipes or something like that. So we need them to transport liquids over a longer distance. So there these are used, these skeleton patterns. Okay, so because making even wood pattern this big is not good idea. Okay, so that is about patterns. Then you know we studied something called as allowances, and that is the interesting topic. Okay, so something called as pattern allowances. Okay, so there are like 5 6 types of allowances, and we'll see each one. So first is the most famous one is shrinkage or contraction allowance. Shrinkage or contraction allowance. So this is this type of allowance is required to be given because because of inherent nature of each material, which uh, which is like uh, you have to when 1 second. 1 second. So yeah, when you have liquid metal, when you pour it, you know this famous curve, right? Yo. So if it is a pure metal, it will have almost isothermal phase change, and then you'll have uh, so this thing. Okay, so pure metal we are talking about. If it is alloy, this horizontal line not will not be like this. It will be maybe something like this, because it is. So this will be for alloys. But okay, so for the sake of discussion, let's consider this as a metal, and yeah, it will be something like this. So you will not have isothermal phase change. You'll have some uh, non-isothermal phase change. Temperature variation will be there. So this shrinkage allowance is divided into three types. First is called as solidification. Sorry, here it will be liquid shrinkage. So you need to consider this also. Then you have solidification shrinkage, and then you have solid shrinkage. Okay, so you have to add all these three to get the shrinkage allowance. Okay, so that is what this shrinkage allowance is. Okay, so it's not a single component system, and this is typically temperature versus time plot, and the direction should be here because you are cooling it. Okay, so uh, yeah, okay, so these three types of shrinkages are there, but not all of them you can consider while giving the pattern. So what is done is we'll see tomorrow's or next week's class that these two shrinkages are provided or compensated by riser. So this is one component of your gating system which is called as riser. So it has basically liquid metal for longer time, and it will compensate for liquid shrinkage and solidification or shrinkage during phase change. And this is where you consider your mean shrinkage allowance. Okay, so shrinkage is three types, but shrinkage allowance is considered only for primarily for uh, solid shrinkage. Okay, so that is one thing. And typically it is expressed as a linear dimension. So it's basically some mm per some meter length, so like that. So whereas these are typically mentioned as percentage of shrinkage volume. Okay, so let's take one example, because we'll have example in this topic only, not in other ones. So the thing is, okay, so you have a, let's take the question. Okay. Okay, so basically, okay, let's take this question first. We'll take more number of questions from this topic, because, as I said, this is the one which will have questions. So before that, let me drink some water. Okay, so it is mentioned that you have a cubical casting of 50 mm size undergoes volumetric solidification, shrinkage of 4%, and volumetric solid contraction of 6%. No riser is used, and pattern making allowance is not considered. Then what is the final final size of the casting? Okay, so this is the question. So see, the trick here is, I told you, if it is not in, like, usually it is in mm per meter, but here it is not, right? Here they're all talking in volumetric and volumetric things. So first thing is, you have to calculate the it will be less, but what do you expect is 50 cross 50 cross 50 mm cube, right? So that is 125 and 30. This much mm cube is expected. Okay, but what happens? It undergoes 4% volumetric solidification shrinkage. So during the phase change itself, it undergoes 4% shrinkage. So volume after solidification is 1 minus 0.04, right? Into, let's say, if this is your V1, right? Because that is the first shrinkage. So basically 0.96 into V1. Okay. So how much that comes out to be? 1 second. 0.96 into 12500. So this is 120,000, 1,20,000 mm cube. Okay, but then they have said that then there is solid shrinkage also. Okay, solid contraction, which is 6%. So volume after solid contraction is, if this is your, let's say, V2, then this will be 1 minus 0.06 into V2, right? Because you have to undergo 6% more. That is essentially 0.94 V2. And if you do that, you should get the answer, which is 112800 mm cube. And then final size of the casting comes out to be, cube root of this 112800 cube root. If you calculate this, you should get 48.3 mm. So you see, since you did not provide any this thing, right? Any allowance, shrinkage allowance. So you'll not get casting of 50 mm side. You'll get casting of 48.3 mm side. Okay, so that's the problem if you don't give any shrinkage allowance. Okay, then this is like the typical problem. But before moving forward, you should note one thing down, because typically what in general, this shrinkage allowance is considered as a positive allowance. So what I mean by positive is, you give additional allowance because you know eventually the things are going to shrink. So if you want a 50 mm casting, you make it pattern, you make it 51 or 52, like that. Okay, so you have a positive impact on your pattern making dimensions. But there is one big exception to it, which is the material which is called as except gray cast iron. Okay, so this is the exception for this rule, because I mean, you have to consider that this guy typically expands during liquid cooling and solidification process. So during these two cases, these two processes, it uh, expands and it contracts during solid shrinkage. Okay, so this is this is a very favorite topic of GATE examiners. Okay. So basically, it may happen that for gray cast iron, you will, instead of getting total contraction, you will get total expansion. So in that case, it becomes negative allowance. So you have to give lesser the size than you actually want. But that is especially for gray cast iron. And there are some problems also on this. Okay, I'll just tell you. I saw some previous year problems. Let me just check. So so this is 2004 GATE question, and they did not mention whether it's positive or negative. So they just mentioned that gray cast iron block and the size dimensions are 200, 100, 10 mm are to be cast, and they just mentioned that shrinkage allowance is 1%. Then ratio of volume of pattern to that of casting will be. So typically this ratio will be greater than 1 because casting is always bigger than, pattern is always bigger than your casting. And the options were also like that only. Second is 0.99, third is 1.01, fourth is 1.03. So if you know the basic of shrinkage allowance, you will either tick 3 or 4. Okay, but the trick was this: they mentioned the grey cast iron, and you have to consider negative shrinkage allowance if nothing is mentioned in the question. Allowance for grey cast iron. Okay, if nothing is mentioned in the question. Okay, so that is the trick, and I think they have asked this question like 2-3 times, not in GATE, maybe some other competitive exams also. So here what happens, you have to make pattern which is smaller because grey cast iron in general expands during solidification process and the whole thing effectively. Okay, so therefore and now see, they have given shrinkage allowance as 1%. So now the question is whether it's volumetric or linear or anything like that. So as I told you, typically it is linear dimension. If in question it is mentioned as volumetric, then only you take it volumetric, otherwise it's linear. So shrinkage allowance for, so there are 3 possibilities: length, then width and height, right? So 3 dimensions are there. So for length you have to consider 200 into minus 1% is 0.01, so that is minus 2 mm. For width, which is 100 into minus 0.01 minus 1 mm. This is 10 into minus 0.01, which is minus 0.1 mm, right? So these are your final dimensions, or not final, but I should say these are your pattern dimensions, which are 200 minus 2 cross 100 minus 1 cross 10 minus 0.1. So 198 into 99 into 0.9. Okay, so all are in mm. So this is your pattern. So volume of pattern becomes, multiply these all 3, is nothing but 1.94 into 10 to the power 5 mm cube. Okay, you can calculate exactly, and your volume of your casting, which is already given, which is 200 into 100 into 10, that comes out to be 2 into 10 to the power 5. And they are asking this ratio, right? Let's say this is VP and this is VC. They are asking VP by VC, and here you can see it is less than 1, right? So 1.94 by 2 is nothing but 0.97. So the correct option was this. Okay, so many people made mistake here because they did not pay attention to the grey cast iron part. So if it is mentioned as grey cast iron, and if they have not mentioned anything else, you know, uh, then you have to take it as negative shrinkage allowance. Okay, so let me just check if any other question was this same category. There is one more. 1 second. Hmm, 1 second. 96 and so again from this linkage allowance, same question, but again they have tricked students, or let's call it as a question, which is grey cast iron block of size 100 mm by 50 mm by 10 mm with central spherical cavity of diameter 4 mm are sand cast. Okay, the shrinkage allowance is 3%. Then ratio of volume of pattern to volume of casting is, and they have not given options also. This was your data entry question in GATE exam 2016. So here again the trick was you need to understand it's a grey cast, so shrinkage allowance will be negative. But now they have added some complexity by saying you know uh, there will be central cavity. Okay, so now students may get confused in this part. So we have central spherical cavity of diameter 4 mm. What to do about this? No need to do anything, because the thing is, when you make pattern, you only consider external dimensions. Okay, uh, for this central cavity kind of thing, you have to consider the core dimensions. So since they are not talking about core, you should not bother about uh, this thing, cavity thing, because you can't do anything about that when you make pattern. To make cavity, etc., you have to put core, and if you don't have that, since they're not asking the questions, you have to consider external things. So uh, so your volume of your pattern. So now we see there the allowance is 3%, right? So your 100 minus 3% of 100, so that is 3. So that is 97 mm, right? Then 50 minus 3 by 100 into 50. So that will be 0.97 into 50. So that comes out to be this into this comes out to be 48.5 mm into I should not say this as volume of pattern, dimensions of pattern, that will be correct. And then this 10 mm will be 3% of 10 mm. So basically 0.97 into 10, that is 9.7 mm. So your volume of pattern, which is VP, is 97 into 48.5 into 3. Oh, sorry, not 3. 9.7. So that is 45633.65 mm cube. Okay. And what is your volume of your casting, which is VC 100 into 50 into 10. So that is 5 into 10 to the power 4, so 50,000 basically. So they are asking you about the ratio. So VP by VC they are asking. So that is 45633.65 by 50,000, and that comes out to be 0.913. Okay, so this was the correct answer. Maybe you'll have like 10% plus minus range because it's a data entry type of question, but exactly it should be 0.913. So you see, you have to make your casting in such a way that it's way smaller than that. Okay. So these are regarding the grey cast iron. Okay. So keep in mind, grey cast iron, your allowance becomes negative. Hold on. Okay. So let me see if any other question is there. In your previous year assignments also we can check. Yeah, so I'm just seeing your assignment. If any numerical is there on this part. But I don't think so. Yeah, no numericals. Okay. So let's move on. And let's go to the 1 second. I think there was one more question. Second. You get it's a similar kind of thing. So let's go to the next type of allowance. So we are discussing allowances. The first one was shrinkage allowance. and for it's a positive allowance, but for grey cast iron it is a negative one. So keep that in mind. Then second one is draft or taper allowance. Draft or taper allowance. It is mentioned as degree Celsius, not degree Celsius, degrees, like angle, I mean, degrees or angle per vertical surface, or maybe I should write per. Okay, so uh, you know what happens is, if you have, let's say, simple uh, casting product to be made, which is like this, and you make a pattern with this thing, uh, and let's say you pour liquid metal, etc., and finally you want to remove this. So what happens? It's not that easy to remove this part, okay? But instead, if you just give some taper or draft on the vertical surfaces like this, what you can do, you can easily remove this guy from your sand, because it's easy, right? Because like there is no friction which will try to uh, I mean, there will be friction, but it will be not in the direction vertical. It will be slightly tilt, so less. So this is easy, right? So the taper that you provide here, usually it's a symmetric taper, so they provide only one value. So this theta is called as basically your draft allowance. And you know, this is for ease of removal of your pattern. This is also, you know, relevant for vertical surfaces. Okay, so it's not on horizontal surface or tapered surfaces. Typically for vertical surfaces, this is given, and then you can machine it off. So whatever extra material you have, in the end you just machine it off. Okay. So this is also positive allowance, because you make your pattern bigger than your actual casting, because then you have this extra material, right? This is extra material, so that you remove. So therefore, it is positive allowance. So these are typical things. Okay. Then third one is machining allowance. Okay. So what does machining allowance mean? As I just said, you just have to machine it off. So in this case, what happens? Uh, in casting, uh, typically very good surface finish is not observed. Okay, so you'll get average kind of surface finish, and then machining is required, like buffing or that kind of thing, and therefore you give the allowance. So this is also you know for surface allowance. So it is not like only horizontal or vertical. All surfaces you have to give machining allowance. Typically given in mm per meter of your surface. Okay, that is the typical units. So, for example, if I take, example, I am giving, okay, for a casting of 200 by 100 by 10 mm, 1% machining allowance is given on all surfaces. Then volume of pattern is times volume of casting. So again, you have to find the fill in the blanks kind of question. So this type of question is pretty straightforward and can be asked. So you can just draw the casting, no? So if it is 200 dimension and this is 100, okay. Let's say this is 200, this is 100, and your height will be, let's say, 10. Then on each surface you have to do finishing, right? So each surface will get increased by 2 mm, no? Because top and bottom. So 200 length you have uh, this side also. I mean, if you machine it from this side and this side, you have to get 200. So 1% from each side. So for pattern, you have to give additional 1% here as well as 1% here also. So that is 2% into 200 plus 200. Okay, so that is 1.02 into 200, that is 204. Yeah, 204 mm. Similarly, this is your length of your pattern. Width of your pattern will be 1.02 into 100. That comes out to be 102 mm. And height of your pattern comes out to be 1.02 into 10. So that is 10.2 mm. Okay. And therefore your volume of your pattern, which is, let's say, VP, is 204 into 102 into 10.2. So how much that is? 204 into 102 into 10.2. So that is 2 point, oh sorry, not 2.212, 241.6 mm cube. And your volume of casting is 200 into 100 into 100. That is nothing but 2 lakhs. And what they're asking is what is the ratio of your pattern to the casting. So VP by VC is, if you just do this, comes out to be 1.061. Okay, so this was your answer. Okay, so like this you have to solve these type of questions. So this is about the machining allowance. Then you have shaking or wrapping allowance. Okay, so this is fourth one, which is shaking or wrapping allowance. Oh, yeah, sorry. Okay, and as the name suggests, this is like for the ease of removal of pattern. this type of allowance is given, but it is also related to vertical surfaces. Okay, so uh, significant or relevant, maybe relevant is the correct word, relevant for vertical surfaces. Okay, and this is the only negative allowance. Why? Because here your pattern will be bigger, right? Because you shake, right? So you increase the volume required for pattern as compared to actual casting. So therefore, it is the only negative allowance, and it is compulsory allowance. But you know that earlier we saw draft allowance, that is optional. So this type of question is also asked sometimes. Okay. Then you have this thing. Fifth one is distortion or camber allowance. Okay, so as the name suggests, you know uh, what happens if you want something like this to be casted. Okay, assume that these are vertical limbs, but it doesn't work that way. What happens when it solidifies? It typically, you know, bends inwards. So to avoid this, what is typically done is, for such limbs, typically vertical or which are prone to the shrinkage kind of defects, you make the pattern like this. Okay, the horizontal ones remains as it is. So this is your pattern, and that is, we have given the distortion allowance, and this is your actual casting. Maybe I should not show it here. One second, I'll show it here. Yeah, this is your actual casting. Okay, so you get the idea, right? Whenever you have these kind of structures where you have limb or higher mass at the top, etc., you give this distortion or camber allowance, and this is like neither positive, neither positive nor negative allowance. Okay, so that is there. Okay, so these are different allowances, and yeah, we saw some examples also. Just see if we missed anything. Yeah. Then we move on to, oh, it's 7:25. So I hope this is clear for you. Then uh, it was about the sand ingredients and sand testing methods. So these are typically uh, one-liner questions. So you know theoretical type of one-liners. No numericals basically, because this is like database things. So one second. I mean, there are no really questions or numericals on this. It's just a data entry. So, or if you know, you know. Otherwise, you don't know. So, uh, you know, what are different molding materials? So, one of the largest one is molding sand, and you know, there is one note here. I mean, we are talking about molding materials now. So, that is the broad topic. And on an average, 1 ton of casting may require 4 to 5 tons of molding sand. Okay, so that is an average estimate. This range can be from 10:1 to 0.25:1. Why am I showing it like this? Like 0.25:1 to 10:1. So this is your sand to metal ratio. So on an average it is between 4 to 5, but it can be as low as 0.25 or it can be as high as 10:1. So that is one important number. It will be directly asked in your one-liners. And most common sand is silica sand. So this is most common type of sand is silica sand. You all must have seen this somewhere. Granules type of structure, and depending on the distribution of these granules, flowability, permeability, compactability, etc. depends. Melting temperature, you know, uh, not melting, but they call it as centering temperature is around 700 degrees Celsius. So therefore, it is very good option for casting process because typically we don't go that high temperatures for metals to solidify. Okay, melting point temperatures of metals or alloys are typically less than that, so we can use sand for making the casts, making the patterns, molds. Then there are some desired properties of molding sand, and these were already discussed, so we'll not go into all of these because it will take a lot of time. Okay, so you can refer to the notes, but some of them are refractoriness, green strength, dry strength, hot strength. So this green, dry, and hot you'll see everywhere in this course. So green means it is like casting. Green means it has moisture. Dry means moisture is evaporated, and hot means even higher temperature than this when you pour the liquid metal. Okay, so that is what it is. Permeability. Since these molds are porous structures, they will have permeability. Permeability is the ability with ability to resist the flow of fluid through the porous medium. Then you have collapsibility, cohesiveness, flowability, adhesiveness, reusability, etc. So those things are already discussed. Then there were some ingredients of molding sand. Typically you'll have sand plus silica, sand plus clay, and water, because clay is like acts like binder, and water you'll have for mixing purposes. Then after silica sand, there are different type of sands like Bolivian sand, zircon, chromite sand, etc., etc. But leave it. Then you have clay as the binding agent. Clay typically is the binding agent in your molding materials, and it's very common. So common binding agent is typically clay. It's cheap. That is the reason. You have fire clay, then bentonite, uh, sodium bentonite, calcium bentonite, etc. And then you have water. I mean, water is clay is activated by water. So on its own, it is not a binder. It is activated by water, 2 to 8%. Okay, so for clay to become binding agent, it needs 2 to 8% water. Then there are some other additives, typically depending on what you want, you can put them, but let's not go there. Then typical sand testing methods. Uh, One is grain size test. So basically, you try to find the grain size distribution among your sand, and you know, uh, finer it is, it will have higher grain fineness number. So you know that is another one liner. Finer sand leads to higher, or it will have higher grain fineness number. Sometimes they call this as GFN. Okay, so keep that in mind. There is a formula for that, but it's basically weighted average of different particle sizes in your sand, and the weight is taken by some multiplier that is already given in the table. So you need not to mark those things. Then there is clay content test. Basically, they put your sand in water, mix it well, and then allow it to settle. So since sand is denser, it settles down, but the clay is kind of a colloidal solution. So you can clearly see two types of layers in that solution, and depending on the height of clay, uh, you what you depending on the height of the clay, you characterize it. Then you can have compressive strength, shear strength, and tensile strength test for your sand. But for that, you typically prepare a cube and test it. Then permeability test, basically you put the sand in a cylindrical or flow kind of a passage, and then you, depending on the pressure that you apply for the air to pass through it, uh, it depends on that, and you get one permeability number. Okay, and yeah, there is a permeability number formula. Sometimes they ask questions on this permeability number. Okay, so this is given as VH by PAT. V is volume of air. Typically, it is 2000 cm cube. Height of the sample, which is 5.08 centimeter. These are standard things. Pressure, it is in your hand. This is air pressure, at which pressure you force the air to pass through the molding sand. Cross-sectional area of your flow channel. Typically, it is cylindrical or circular channel. So you'll have standard is 20.268 cm square. And then this is capital T is time. Or maybe what we can do, use small t, because otherwise you may get confused with table temperature. Time in seconds for this tests. Okay, so if you put this all standard numbers, you get this as your final formula. And the reason I am talking about this is because there was one direct question on this. Let me just find it. If you know this formula, you could have got the answer. Otherwise, no, you could not have done anything in this question. Yeah, so this was 2002 question, and they only mentioned, maybe we'll take the question. Okay, huh? So they mentioned in the question that the permeability of molding sand is determined by standard AFS test. So AFS is, I think, American Foundry Standards, but they just gave the number, and they gave the air pressure as 10 gram per centimeter square gauge, and time taken for air to escape is 1 minute. Then the permeability number is, and there were four options. Okay, so you could have, if you are lucky enough, you could have guessed also. So this was 11.2.4, 100.2, 75.3, 50.1. Okay, so uh, you know if you know this formula, then you can solve this. Otherwise, you can't. Okay, so hello. Okay, if you have any doubts, you can ask. Otherwise, you can text or type also. So yeah. Mm, okay, so this is not t. This is small t. Time. Mm, 1 second. Is constant, is it correct? Let me just check. I have it somewhere. Let me just check. VH by PAT is the correct one. 5.08. Mm, 1 second. Permeability number. Because what the problem is, these American standards, they typically tend to use different units. Like they'll not use uh, kilometers, they'll use miles, like that. No. So let me just confirm once. 2000, and this is gauge pressure. Okay, so this is also one. This is not absolute pressure. This is gauge pressure. But having said that, mm, volume is 2000 centimeter cube. This is centimeter, gram, yeah, I mean, see, we can find this constant here only. Volume is 2000 cm cube, height is 5.08, and cross sectional area is 20, right? So, what is that? 2000 into 5.08 divided by 20.268. Yeah, so 501.28 is correct. And then if you divide by 10 and divide by, oh, the time is not in seconds, okay, it is in minutes. Yeah, that is why we are not getting the answer. This time should be in minutes. Yeah, then it's fine. Then in that case, this permeability number, or let me use Pn because P is already pressure there. Pn is nothing but 501.28. Pressure is 10 gauge. Time is 1 minute. So you have 50.13. Okay, so this option is correct. Now, this was directly formula based. If you don't know the formula, you can't do anything. You are stuck. Okay, so that is about one more type of numerical that can be asked. Then after that, in testing, then there are some other tests, etc. But that does not have any numericals, etc. It's just the theory. You can revise it. Then we went to sand molding, etc. Then you have sand molding, investment molding, ceramic molding, plastic molding, graphite molding, and all those kind of things. Uh, then there was something called as die casting. Die casting is nothing but solidification of molten metal, but under pressure. Okay, so there you'll have hot die casting, hot chamber die casting, or cold chamber die casting. These are typically used for die casting. Uh, solidification under pressure. So basically, it is in casting you have atmospheric pressure, but here you'll have solidification under external pressure. Under external pressure. Okay, and then you'll have this hot and cold die casting. But hot means typically it is the solid metal is molten in the chamber itself, and then pressure there itself is applied. In cold, you melt it somewhere in another furnace and then bring it to the pressurized chamber and then solidify. And these are typically used for low melting temperature materials, because what happens in casting, if some metals have low melting points, by the time you take them out from the furnace and put it in the casting, they solidify, so you don't have much time for transfer. So therefore die casting is used. And typically non-ferrous alloys kind of things, non-ferrous metals and alloys like tin and all those kind of things, tin, lead, etc. Centrifugal casting, you should read it up because it's interesting. You'll have different solidification rate at different radius from the center, and that gives you variable properties in your centrifugal casting products. Okay, so this is also very interesting. You can study more about it, but you'll have variable properties as per distance from the center. Okay, so like that. And then there are different things, not very important. And in the last we discussed about cores. So cores are basically materials used for making cavities, internal features, which cannot be produced by patterns alone. So in one of the previous problems we saw, right, they had given external dimension and one insert, that graphite problem, the grey cast iron problem, where they had given outer dimensions, but one hole was also there. So that hole you can't make by this thing. What do you say? Pattern. You have to use core for that, and So regarding the core, for example, one kind of question that can be asked, numerical kind of thing. What happens? Let's say you have this kind of casting, and this is your core. So core is also made up of sand, okay, but it is like sintered at very high temperatures, so it won't typically dissolve when your liquid metal solidifies. So what happens? This is your liquid metal, right? Okay, around the core. This is your core. So it experiences buoyancy force. So sometimes they ask this also. So net buoyancy force experienced by the core is given as rho m minus rho c into Vg. So rho m is a melting of density of melting liquid, rho c is density of core, and you know volume of core is V, and then you have G. So sometimes they ask this type of simple questions also. Then they use core prints. So basically core prints are used to position the core correctly. So these are standard one-liners. Core prints are used to position the core properly. Okay. Then you have chaplets. Chaplets are used for supporting core in inside the cavity. So as I said, core experiences buoyancy force, so there is a chance that it may get displaced, and to avoid that, what they do is, whatever liquid metal is there, they will use certain supports like this. Okay, certain supports like this, and these are called as chaplets. And what happens? These are of same as molten metal. These are made up of same metal as molten metal. And what happens when this liquid metal solidifies? These chaplets become their integral parts, so you need not have to remove. And the thing is, one may ask the question that what if the chaplet itself melts, because you have a liquid nearby which is at equilibrium melting temperature. But even if it melts, usually what happens? Solidification starts at the core and the inner boundary of your pattern or cavity. So typically, those problems don't come with chaplet as long as they don't lose contact with your core and the casting. Okay, so then there were some desired characteristics of cores. Again, not much from comparative or numerical points of view. And you can study different kind of cores, but again, not that important. Hanging core, cover core, wing core, etc., etc. But yeah, I mean, these are not that defect. Then there are some core defects, etc. But you can revise. These are theoretical topics. Okay. So yeah, more or less we covered all of the topics. So then yeah, that's it for this week. Next week we'll see some gating design, etc. Those things, and that will be more numerical oriented. Okay. So we'll stop here for the day, and we'll continue in the next class. Okay. Bye. Yeah, the CO2 molding also discussed in the class. Chaplet also discussed. Yeah, this investment casting also. You basically use wax, and this is for mass producing complex geometry, etc. No, pattern material is not sand, it's typically wax. So that option is wrong. Sawdust, I think, is for B and C collapsibility, etc. But yeah, the due date is 780, so we should not discuss this. So yeah, that is that. One second. Can you revise the formula for permeability of mold? But yeah, you already left. Yeah, so we discussed that. Basically, you have a certain volume of air at certain pressure, and that certain finite volume of air is made to pass through a porous mold structure. Then you measure how much time it took for that complete air to get passed from that mold. Okay, so that is the main thing. One second. Okay, so we'll stop. It's already 8.